Morning.
Minor. Okay, guys. So how is everything? Now, before we start, any questions? Now I have a question. Do you guys want to do a review today, or should we leave that for tomorrow? Yes.
Tomorrow?
Tomorrow.
Okay. Just before starting, guys, I may have to finish the class a bit early today. I have an appointment that I need to get to, so you guys will be off by 12:45-ish. Okay, so okay. Any burning questions before we start? Yep. Okay. So, guys, what we will do is start off with chapter number 10. Okay. And chapter number 10 is about primary SOK 2-3 things. We have what we call axial resolution, we have the lateral resolution, and then a last point, which is going to be focusing. Okay. And focusing, where we already briefly talked about that in chapter 9, which we can say okay was related to the beam. Okay. So, first of all, resolution. And guys, this is going to be a question that's question. This is going to be a term that you will hear being brought up not only in this chapter, but chapter 12 as well, chapter 13 as well, and even to chapter 15. Okay, so it will be of an utmost importance to understand what is it that the word resolution means. Now, guys, resolution mainly it simply just means accuracy. As far as we are concerned, an ultrasound or ultrasound physics, whenever we see the word resolution, what is going to mean? It's going to mean accuracy. Or we can also say the ability to accurately display Did that make sense?
Yeah.
Okay. Now, if any of you would like to, yes, okay, contribute and tell me, yes, okay, what do you think of the word accuracy? Don't look in the book. Just if a week ago, if somebody says, okay, accurately or accuracy, what will you understand by that word?
Like something that's like spot on.
Spot on, okay. A simpler word,
Precise.
precise, correct, right? Okay, yeah, okay. So what is it that accuracy is going to mean? And you will see that, for instance, yes, okay, if I say, well, okay, yes, well, let's say that, okay, as we are scanning a structure, let's just say, okay, that has the shape of a, that's okay, star. That's okay, probably. Let's say that, okay, yes, we are scanning a structure which is, let's say, round. It's round and this is its shape, this is its size. And not just that, okay, this is going to be, yes, okay, you can see in terms of anatomy, this is going to be its location. Now, if the system is able to, yes, okay, let's say, okay, it lies at a depth of, let's say, between 1 and 2 centimeters. Now, if your system is going to, yes, okay, be accurately or correctly displaying a structure that looks like it's going to look like, or that it actually was, in terms of its shape, that it actually is okay, also is correctly located. Okay, that will mainly mean that, okay, as we have had a good resolution or that our image is accurate. Whereas, okay, as let's say, as okay, if the structure that we scanned was circular, but that it appears, let's say, as okay, let's just assume that's okay, like a square. Not just that, okay? Okay, so here is okay, it is in a wrong shape. Maybe it's okay, it's also it's okay, placed at a wrong location. Practically, it's okay. Actually, it's okay, it was located here, but we see it here. Okay, things like that. Where, okay, yes, what you see on the image is not accurately or precisely or correctly representing the anatomy that you are scanning. That's mainly going to mean that, okay, as we have had a poor resolution. Did you guys get that?
Yeah.
Right, okay, okay. So in case that your scanning doesn't match or is not accurately or correctly displaying, yes, okay, what the structure looks like, that's going to be, yes, okay, a poor resolution. Or we can say, okay, yeah, low accuracy. Did that make sense? Okay. So resolution means accuracy or ability to accurately, yes, okay, display a structure in its actual shape, location, shapes, etc., 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 etc. Clear? Okay, on numbers. Okay. Whereas, okay, if that's not the case, that was going to be as okay, poor resolution. You can say, okay, inaccurate or incorrect. Did that make sense? Okay. Now, guys, although in this chapter here is okay, your book mainly only has okay, at least for this chapter here, sorry. In chapter 10, it mainly has okay, just talk about two resolutions, which is the actual resolution and lateral resolution. But what I like to do is mainly as okay, just give you guys what we can call it, a short intro into our different resolutions. Okay, so as far as resolutions are concerned, that's okay. We can mainly say it's okay that we have two major types of resolutions. Two major types of resolutions. One is going to be yes, okay, spatial resolutions. So we can mainly say, okay, resolutions in terms of space. And the other one is going to be temporal resolutions. Is that clear?
Yes.
Yeah.
Right, okay. So as you see, it's okay, similar to your intensity, it's okay, so is the resolution going to be spatial and temporal, where the term spatial may just mean as okay, mean because it's okay in relation or pertaining to space. Whereas, okay, as on the other hand, your temporal mean is going to as okay, mean in relation to time. Did you guys get that?
Yeah.
Okay. So spatial is going to be as okay in terms of space. Temporal is going to be as okay in terms of time. Okay. So you have time spatial resolutions, we have temporal resolutions. Now, guys, just to yes, okay, make it simple. That's okay. Your temporal resolution, yes, okay, that's going to yes, okay, be relevant when we are looking at a structure which is in motion. For an example here, for instance, okay, be the beating heart. Clear? Okay. Okay. Or yes, okay, even things such as a Doppler. That's mainly going to be as okay, very much as okay, dependent upon your temporal resolution. Now, guys, the primary details, okay, the primary details of your temporal resolution, we will talk about that as a whole in chapter 13. So your chapter 13 is nothing more but mainly as okay, talking of temporal resolution. Clear? Okay. But which mainly is going to all be about that's okay, how do we accurately, that's okay, follow the motion or movement of a moving structure on our scan. Did you guys get that? Or more like a movie? Okay, that's why it's okay. They call back in, they may still call it, that they call a movie a motion picture. Because what is it a motion picture is? It means, okay, it's just the pictures that are moving. Or you see that, okay, yes, the thing that you as, okay, follow in the picture actually is moving. That, okay, as a single picture, or a frozen frame, right, okay, is no motion. Did you guys get that? Clear? Okay. Now, guys, the spatial resolution, just okay, guys. Well, because that's okay again. Resolution and the term are related to space. Okay, and we can mainly say, okay, is where this one here is going to be as okay. We can say it's okay, relevant to that's okay, your frame, a single image. Now, as far as that's concerned, guys, our spatial resolution, just okay, we have a couple. That's going to be as okay. The first one that we will talk about, which is going to be as okay, your exit resolution. Okay, so we will talk about this fellow here today. Another type of yes, okay, your spatial resolution is going to be what we will call a lateral resolution. Okay. And yes, okay, although in this chapter here, but yes, okay, we may talk about this at some point, yes, okay, after our quiz. Other kind of okay, yes, what comes on this okay, axial resolution, sorry, spatial resolution is going to be as okay, what we'll call the elevational resolution. Okay. And this elevational resolution here, guys, that's going to just okay be talked about in detail in chapter number 12. There's going to be a resolution that okay, yes, strange enough, yes, okay, just go under the name spatial resolution. Okay, although yes, okay, all these here are spatial resolutions because they are all resolutions in terms of space. Last but not the least is going to be yes, okay, what we will call the contrast resolution. Now, the spatial resolution here, guys, is going to be yes, okay, your chapter 15. Contrast resolution is going to be 15 and 16. Is that clear?
Yes.
Okay. Now, primarily, if we take these three fellows here, and compare them up against one another. So we said, let's do this one. We're going to have, okay, that's what we'll call resolution. Now, when we talk about these three, yes, okay, resolutions here, axial, lateral, and elevational, you mainly, yes, okay, are going to hear a term being used that's going to be a numerical value. And okay, as well, we just can say here is last is going to be as okay. Accuracy. Now the three resolutions that we had or have was respectively as okay the EXA resolution, we have the lateral resolution, and the last is going to be the elevational resolution. Okay, guys. Now, when comparing these three resolutions here, your EXA resolution, that's actually going to be the one that has the lowest numerical value. Your lateral resolution is going to have as okay a numerical value which is going to be greater than that of your EXA resolution. Whereas your elevational resolution is going to be the one that has the greatest numerical value. Now, as far as the accuracy of these three here, EXA resolution is always going to be the best. We can say that your lateral resolution is going to be poor or bad. Where, okay, out of the three resolutions, just okay, your elevational resolution is always going to be the worst or poorest. So what does that mean? That will mainly mean that lower numerical value of each of these resolutions here is okay, give you a better accuracy. Where on the other hand, you can say it's okay, the greater the numerical value, the poor or bad is going to, or worse is going to be the accuracy. Did you guys get that?
Yes.
Okay, okay. So we weigh as okay as we go over each of these resolutions here, it's okay. Talk about it's okay, what's going to be the accuracy, what's going to be it's okay, what determines the numerical value of your resolution. Now what you mainly will see that okay is that for your spatial, EXA resolution is going to be lower than that of the lateral resolution, which is going to be lower than that of the elevational resolution. Okay, but what you mainly can say is okay, that the greater the numerical value, the poorer the resolution. Or lesser is going to be the accuracy in some of that resolution. Okay, now guys, since they are all spatial resolutions, since they're all spatial resolutions. Okay, they were all just examples of spatial resolutions. That's how it's okay. And we can mainly say it's okay that the numerical value is going to be used expressing or going to be expressed using a unit of a spatial value, which is going to be any unit of distance. So something like as millimeter, for instance, yes, will be the unit for the numerical values of each of these resolutions here. Okay. Now, what would be the numerical value of your axial resolution? The numerical value of your axial resolution actually is going to be equal to the spatial pulse length divided by 2. The numerical value of your lateral resolution, that is going to be equal to the width of the beam. And the numerical value of your elevational resolution is going to be equal to, or is going to be the same as the height of the beam. Is that clear?
Yes.
Okay. So when we look at these two fellows here, your lateral resolution and your elevational resolution, they are mainly both of them are going to mainly be related to the size of your beam or the measurements of your beam. Whereas when we look at the axial resolution, we can mainly say that this is going to be dependent upon the size of your pulse. Clear? Okay. So the size of your pulse is going to play a vital role in determining your axial resolution. Where the width of the beam and the height of the beam is expected to going to determine the lateral resolution and elevation resolution of your beam. Okay, so these numerical values here, are mainly going to be compared to the distance between reflectors or structures. That will determine, are we going to have a good resolution or are we going to have a bad resolution? Okay, because just because I said, axial resolution is the best, lateral resolution is the poor, and elevation resolution is poorest, that doesn't mean that you can't get a poor axial resolution. You can get a poor axial resolution. Okay. You can also get, as a poor lateral resolution. You can also get a poor elevation resolution. Okay, but by comparing the three on here, it's okay, the same as it's more likely going to be that per standard, yes, okay, exit resolution is always going to be the best out of the three. Clear? Okay. Okay. But that doesn't mean that you can't get a poor exit resolution. Of course you can. Okay. Okay. Likewise, can you get a poor lateral resolution? Yes. Can you get a good lateral resolution? Of course you can. Okay. Otherwise, it would have been doomed from the beginning. Okay. That it always are going to be as okay poor or bad resolution. Okay. So you can get a good lateral resolution as well. Okay. Just because if we say as okay, your elevation resolution is the poorest. Okay, that doesn't necessarily mean that you always are going to have a poor or a bad elevation resolution. You can get a good elevation resolution as well. Clear? Yeah, no, just give me a second, guys. Okay, guys, sorry. Did you guys get that? Okay. So are you guys ready, Betty, and steady to talk of the exit resolution? Exit resolution. Now, what we mainly could say about yes, okay, exit resolution is once we say yes, okay, the word resolution. Yeah, okay. We could say yes, okay, that the ability. And we can say of the ultrasound system to accurately display. Now it's going to be yes, okay, we can say yes, okay, two structures that are parallel to the beam's main axis. Now, guys, although it's okay, I don't personally like this definition here, but it's not about my personal liking or dislike. Clear? Okay. But let us just say, it's okay. Well, first of all, it's okay. What do we mean by the beam's main axis? Now, guys, if this here is your transducer, if this here is okay, was your transducer, we could say that okay, yes, if this here is okay, is the beam. Although as okay, we may see later on that okay, as your lateral axial resolution, sorry, actually as okay is going to be determined by as okay your spatial pulse length. But we can mainly say okay, if this for instance okay was your beam, then this here, this is the beam's main axis. which we as okay on a scan may as okay see that for instance okay this here is okay was our scan. This is where we have our transducer. And okay, yes, we can say okay. At this instant of time, yes, okay, this is our beam. So this is going to be as okay the beam's main axis. Okay. So it all is okay about is okay the ability of the system to accurately display two structures that are located parallel to the beam's main axis. Or this parallel to the beam main axis can also be as okay rephrased as front and back. Where we can mainly says okay. We see if this here is okay was front. And we can say it's okay, this one here would be back. Or on a scan is okay. If this here was back, then this one here would be front. Or we can say shallow and deep. Did you guys get that?
Yeah.
So if we find yes, okay, we're scanning two structures, let's say, okay, sorry, that they were located like this. One was at a shallow depth, and we can say it's okay, one was at a deeper depth. Or because as I go, one was in the front, one is in the back. Clear, okay? Or we can say, okay, parallel to the beam's main axis. And we see these two scans, yes, okay, separately, yes, okay, displayed, accurately displayed. That they appear as okay as the actual size, that the ear can appear as okay as the actual distance from one another. Okay. And okay, as that they're correct in their shape, their size, and okay as locations. That would have meant that okay as we would have had a good axial resolution. Yeah. Whereas if these two structures here is okay, does not appear as two separate structures, but as okay, we smushed together or mixed together, or that okay, yes, they may be as okay, physically as okay, not accurately placed, but actually as okay, something like this on the scan. Okay, as practically as okay, they were here. On our image, we see them misplaced or something like that. Those will be factors that mainly as okay will tell us that we have a poor axial resolution. Okay, although this here is a more commonly as okay going to be referred to as a poor axial resolution because the two structures which was physically there as okay may appear as one mess or one structure. Okay, so what is that we are not going to be able to do? We will not be able to, yes, okay, Well, okay, first of all, we don't get, okay, as an accurate image because 2, if that shows up as 1, that is an inaccuracy right there. Likewise, okay, because that's okay, we will not be able to just, okay, distinguish between this structure versus this. Okay, which were 2 separate structures, but it's okay, as they appear as 1. So we could not distinguish because it's okay, A from B. Did you guys get that?
Yeah.
But the thing is that, okay, yes, A, yes, okay, one structure is going to be at a shallow depth, the other structure is going to be at a greater depth. Okay, or you can say one structure that is shallow and a structure which is deep, smushed together, appearing as one structure or one big mess. That is going to mean that we have a poor axial resolution. Is that clear? Okay, guys. Now, as I said earlier, now it's okay, these 3 resolutions, axial resolution, lateral resolution, and spatial resolution, what were they? We call them spatial resolution, right? Okay, they were examples of spatial resolution, resolution that was going to be measured in terms of space. Clear? Okay. Then we also says, okay, now all of them are going to have is okay, the same type of unit to be expressed. Unit of space, unit of distance, units of length. Did you guys get that? Okay, so your axial resolution, yes, okay, it's always going to be, yes, okay, expressed in a unit of distance. It says, okay, axial resolution. You guys may see me as, okay, using the phrase AR, AR, AR again. That doesn't mean an automatic rifle. Okay, AR is mine, yes, okay, just my abbreviation for axial resolution. And that is going to be measured using a unit of distance, which can be something like a millimeter. Okay, it can be centimeter. It, it can be micrometer. It can be any unit. As long as it's a unit of distance, it will be, yes, okay, good enough to be expressing your axial resolution. Now, guys, on my earlier slide, I say it's okay that the numerical value of your axial resolution, that was equal to your spatial pulse length divided by 2. Is that clear? Now, guys, if you just look at, okay, yes, the unit of your spatial pulse length, that was the same. Because it's okay, it could be millimeter, it could be centimeter, it could be something like micrometer. Now, whatever your spatial pulse lengths become, when you divide that by 2, that is going to be the numerical value of your axial resolution. Did you guys get that?
Yes.
Right, okay. Which you also can say that, okay, yes, you X the resolution twice equals the spatial pulsenet. Or twice the value of your X the resolution is your spatial pulsenet. Okay. Now, guys, please keep in mind that, okay, what was your spatial pulsenet? What was your spatial pulsenet? Now we say, okay, X resolution was your spatial pulsenet divided by 2, where we could say, okay, what makes up your spatial pulsenet, guys?
Your source and your medium.
Okay, that's what determines it, my dear. What values determine the numerical value or the value of your spatial pulsenet? The number of cycles in a pulse, right? Times the wavelength. Did you get that? Yes, guys.
Yeah.
Chapter number 4, right? Okay. So, Mike, okay, what is it that you can be? You can be given something like, okay, yes, the number of cycles that a pulse have. Let's say it's okay, that a pulse has 4 cycles. And we say that, okay, as each of those cycles has a wavelength of, let's say it's okay, 0.5 millimeter. Okay, where you mainly will say, okay, yes, multiplying these two, yes, okay, what would they give you? They will give you, yes, okay, your spatial pulsenet. So 4 divided by 0.5 actually becomes 2. Your spatial pulsenet in this instance here will be 2 millimeters. Did that make sense?
You don't have to divide it by 2. After
Right now
that?
we talk about your spatial pulsenet here.
Okay.
Clear? Okay. Now when we divide this by 2, that will give us, okay, yes, our numerical value of the X resolution, which in this case it will be 1 millimeter. Did that make sense?
Yes.
Clear? Okay. This will be the numerical value of your exit resolution. But my thing is, okay, let me put it this way. You can be given directly a spatial constant and determine PR to calculate the exit resolution. Did that make sense? Clear? Okay. Or you may be given a spatial, that's okay, the number of cycles in a pulse and the wavelength of each of those cycles, and still be asked to calculate your exit resolution. Clear? Okay, so what will you do then? You multiply the number of pulses by the wavelength. That will give you, yes, okay, the spatial pulse length of that pulse. How long is it that that pulse physically is? When measured in terms of distance or length, right? Did that make sense? And then from that, being asked to just, okay, calculate the exit resolution. So the only thing that you need to know is, okay, is how do we calculate the numerical value of your exit resolution? Because in this case here, it's okay, guys, this 1 millimeter here was going to be, as okay, the numerical value. It's a number, right? Okay, 1 is a number. Clear? Okay. You could have a numerical, you could have had, okay, yes, let's say it's okay, an exit resolution of 2 millimeters. It could have been 1.5 millimeter. It could be 2.5 millimeter. It could have been 3 millimeter. It could be 4 millimeters. So on, so on, so on, so on, so. Right? Okay. When we will have a numerical value of 2 millimeter, that was in case that, okay, yes, the spatial pulse length had been 4 millimeters. Clear? Okay. What could have caused the spatial pulse length to be 4 millimeter? Okay, we could still let's say, okay, we had 4 cycles, but that is okay, the wavelength of each cycle would have been 1 millimeter, sorry. Clear? Okay, so the total spatial pulse length would have been 4 millimeters. Okay, but when we subdivided that 4 into half, that gave us the numerical value of 2 millimeters. Numerical value of your exit resolution being 2 millimeters. And so on. Did that make sense?
Yeah.
Right, okay. So what we mainly can say here is, okay, now out of these two here, well, let's do it this way, guys. Let's say it, okay, as in one case we had, okay, as the exit resolution. Oh, sorry, let me write that. Here. That's it, okay, in case that we have, okay, as an exit resolution. Numerical value, for instance, okay, was 2 millimeters. Right, okay. How have we got that? Mainly by, because that's okay. 4 millimeter is okay being the spatial pulse length divided by 2. Clear? Did that make sense?
Yeah.
Okay. Now, how did we get these 4 millimeters of a spatial pulse length? All determined by 2 factors. How many cycles did we have per pulse? And what was the wavelength of each of those cycles? Did you guys get that? Yeah, okay. Now, in this case here, guys, what we talk about is going to be as okay, the wavelength of the wave produced by the transducer. Clear? Okay. So here is okay, your spatial pulse length is not going to change. In this instance here, is okay, it will remain constant. Okay. Okay. So when we say spatial pulse length here, is okay, that's going to be, what is the spatial pulse length of the pulse produced by the transducer? Did you guys get that? That's going to be, that's okay, what we will be referring to when calculating the numerical value of the axial resolution. Did you guys get that? Okay. So the axial resolution, that is not going to change as we go from medium to medium to medium to medium. Is that clear? Okay. So when we say as okay, an axial resolution, that is pretty much going to be as okay, determined by the spatial pulse length of the pulse produced by the transducer. Is that clear? Okay. So you can mainly as okay, just write that axial resolution remains constant. Okay. Your axial resolution is going to remain constant at different depths. Now we can say it's okay, another resolution, it's a case that you had okay as another transducer, which has okay as another axial resolution with a different numerical value. That's okay, that's okay, say 4 millimeters. How do we get this 4 millimeters of an as a numerical value of the axial resolution? We can mainly say it's okay because we had a spatial pulse length of 8 millimeters that was divided by 2. Right? That gave us, okay, at the axial resolution of this transducer here had a numerical value of 4 millimeters. Okay. Okay. And in this instance here, it's okay. These 8 millimeters here is okay. That was your spatial pulse length. How did you get that? Well, okay, as the number of cycles in the pulse and the wavelength. Likewise here, okay, these 4 millimeters here is okay. That was the spatial pulse length. How do we get that? Mainly it's okay based on it's okay, or determined upon it's okay the number of cycles in a pulse and the wavelength of each of those pulses here. Or cycles, sorry. Did that make sense? Okay. But what we just see here is okay that in one transducer, what do we have? This one here have a low numerical value. Let's say it's okay, and this transducer here is okay, it has an axial resolution with a great numerical value. Did you guys get that? Clear? Okay. Now, guys, we are going to talk about how is it that, okay, yes, these transducers are just, okay, these transducers here with their spatial pulse length, with their numerical value of your EXA resolution, may give you as, okay, either a good EXA resolution or bad. Are you guys ready for that? Okay, guys. So what did we say that EXA resolution was? The ability of a system to, yes, okay, distinctly display two structures, front and back of one another, or parallel to the beam's main axis. Or as, okay, or we could say, okay, one was at a greater depth or a shallow depth and greater depth. Now let us say that, okay, yes, in this case here, that we have a structure here and a structure here. Where we can say, okay, this will be as, okay, the one in front, this would be the one in back. Or we could say, okay, this would be at a shallow depth, this would be at a greater depth. Clear? Okay. But right now it's okay, we are talking about circular green transducer. Now, guys, if this distance here between these two structures here, for instance, was 2 millimeters or more than 2 millimeters, this distance was 2 millimeters or more, that will give us a good letter, or that will give us a good EXA resolution. Did that make sense? Did that make sense?
That says distance between structures?
Exactly.
Okay.
Whereas, let's say it's okay, if we had the same transducer, likewise, it's okay, we have two structures. Or if we say that, okay, in this case, it's okay that this distance here between these two structures here is okay, if that distance was less than 2 millimeters. That would actually is okay, have led us to a bad EXA resolution. So if you want to put it in this way and say that, okay, yes, that, or we can say it's okay that if the numerical value is lesser than the distance between the two structures. Okay, that will give us a good resolution. Whereas on the
I thought you said if it was lesser than the distance between the two, then it would be bad.
but that's not what I'm saying here. Yeah, I'm saying that okay, it's the numerical value, this distance here. This is your numerical value right here.
Right.
Okay. If that is lesser than the distance between the two structures.
Yeah, I get it. I read it wrong. I get it.
Okay, that will give you a good axial resolution. Whereas, okay, on the other hand, if your numerical value is greater than the distance between the two structures, that will give you yes, okay, a bad axial resolution. And the thing that you gotta take as okay, look at when we talk to you about the two structures here and two structures here is that okay, yes, that these structures are going to be okay, front to back, or actually it's okay because it's okay shallow and deep. Did you guys get that?
Yeah.
Good. Whereas let's say it's okay that we had this transducer here. The numerical value is okay for this transducer is going to be greater than that of this one here. Okay. But my idea, the concept will still be the same. That okay, yes, because this transducer is okay, produces a pulse that had a spatial pulse then of 8 millimeters, which okay, give us the numerical value of the axial resolution to be 4 millimeters. So what that mainly mean? That mainly mean that okay, if the distance between yes, okay, these two reflectors here, or these two structures here, where one is shallow, one is deep, one is in front, one is in back. If this distance here is okay, this distance between these two reflectors here was 4 millimeters or more. This transducer here will still give you as okay, good axial resolution. Clear? Okay. Whereas, okay, as if this very same transducer here scanned, and okay, yes, that is distance between, yes, okay, two structures that we were scanning. If this distance here is okay was less than 4 millimeters, that will still lead to, yes, okay, a bad exit resolution. Did you guys get that? So, guys, the distance between the reflectors or structures have to be compared to the numerical value of the resolution that you're talking about. Clear? Okay. So if the numerical value of whichever resolution, if the numerical value is lesser than the distance between the two structures, you will have a good exit resolution. Or if the numerical value is greater than the distance between the two structures, you will have a poor resolution. Clear? Okay. But when we talk of exit resolution, that numerical value is going to be determined or dependent upon your spatial pulse length. Did you guys get that? Yeah, okay. And what's going to be as okay, your exit resolution is going to be as okay, the ability of the system to accurately display two structures or distinguish display structures where one is shallow, one is deep. Or your book may say is okay in front and back. Oh, yes, okay, as I don't like it, but just okay, since it's there, well, okay, parallel to the beam's main axis. Did you guys get that? Now, although I said it, I never said it. Well, this is one of those chapters that, okay, yes, I would have liked to have done in the class or physically in the classroom. You will see me dancing around, but that's fine. Okay. I may need the exercise anyways. So, yes. Okay. So, any questions? So, whatever your spatial pulse length is produced by the transducer, half of that length is going to be your spatial pulse length. But what we mainly can say is, okay, yes, the greater your spatial pulse length, the greater will be the numerical value of your exit resolution, right? You take a greater number, divide that by 2, you'll still get a greater number. Compared to, okay, if you take a smaller number and divided that by 2, you get a smaller number, right? Clear? Okay. But those will be the numerical values of your exit resolution. Clear? Okay. But, to determine, does this numerical value of my exit resolution, did that give me a good exit resolution or a bad exit resolution? You have to compare that numerical value to the distance between the two structures. Clear? Okay. Now, if the numerical value of your exit resolution is lesser than that distance between two structures that are shallow and deep, front or back, or parallel to the beam's main axis, you will get a good exit resolution. Whereas, if the value, or if the numerical value of your exit resolution is greater than the distance between the two structures, shallow and deep, front or back, or parallel to the beam's main axis, you will have a poor exit resolution. Did that make any sense? So straight, as you can say, okay, the greater the numerical value of an exit of a resolution, the poorer is it that it will be. Did you guys get that? Now, guys, so what can we say? Shorter pulse, better exit resolution, right? Longer pulse, poor exit resolution. And what we mean by shorter is going to be shorter spatial pulse length. What do we mean by longer pulse? Greater spatial pulse length. Okay, how did we get this shorter pulse? You could get at it because, okay, the pulse had a low number of cycles. And or if those cycles had a low wavelength, right? Did you guys get that?
Yes.
Good. Or on the other hand, it's okay, what will give us a greater spatial pulse length? That would have been either it's okay that our pulse had, okay, as a great number of cycles. And or if those cycles had a great wavelength. Did you guys get that?
Yes.
Good. Okay, so this is straight away as okay, giving you a question and say, okay, which of these two here will have a good axial resolution, or which of these two here will have a bad axial resolution? When we're comparing just, okay, two transducers with longer spatial pulse length or shorter spatial pulse length against one another. Of course, this can never have a poor axial resolution because it produces the long pulse. Okay, and that long pulse is going to just, okay, give us a great numerical value of the axial resolution. Yeah, this one is going to just, okay, produce a shorter pulse, which means, okay, will give us a lower numerical value of the axial resolution. But guys, if I said that, okay, yes, we have two transducers with same number of cycles that produces pulses with same number of cycles, but one have a greater period, one has a shorter period, would you be able to tell me which one will produce a good axial resolution and a poor axial resolution? Which one will produce a poor axial resolution? The one with a greater period or shorter period?
Greater period.
Greater period, because what does that greater period mean?
Greater
Low frequency.
Caitlin, you said something there?
Yeah.
Right, but you said
Greater
okay.
wave.
It will have a greater wavelength, right? Okay, so that greater wavelength, what does that give you? Greater spatial pulse length, right? Where, okay, the one with the lower period have a lower wavelength, most likely lower spatial pulse length, and hence lower numerical value of your axial resolution. Yeah, okay, so don't give me that and say, Mike, the wavelength is not measured. Or okay, you in that case, that's okay, will not be asked to, yes, okay, calculate it. Because okay, what we mainly is okay, what George doing says, okay, saying, well, okay, not wavelength. Or even as okay, if you say that okay, yes, we have a lower period, that lower period mainly automatically will mean that we have a lower wavelength. And lower wavelength will then just okay be a lower shorter pulse, which will give us okay as a lower numerical value of the axial resolution, which will cause that will be more likely to be a better axial resolution, sorry, compared to this one here, which would have had okay as a greater period. Which due to a greater period will have a greater wavelength, Greater wavelength will have a longer spatial pulse length, greater numerical value of the axial resolution, greater numerical value of the axial resolution, more likely it's okay, poorer axial resolution. Whereas, guys, what do we know? And something that I've been talking about again and again and again and again, indirectly is going to become more clear and obvious now, is that the greater frequency and we can mean this, okay, yes, okay, made a greater frequency transducer. Now what we know is that frequency was inversely proportional to wavelength, right? So the greater the frequency of our transducer, the shorter will be the wavelength. The shorter the wavelength, the shorter the spatial pulse length, the lower the numerical value of the axial resolution, and that will be giving us a better axial resolution compared to a low frequency transducer, because due to that low frequency, it will have a greater wavelength, greater spatial pulse length, greater numerical value of the axial resolution, which mainly is okay, will give us a poor axial resolution. Because what would that greater numerical value mean? That we it's okay, we have to have a greater distance between the two for it to be good, which is less likely going to happen. So guys, back in chapter 3, when we talked about the parameters, I told you guys that high frequency transducers are ideal for diagnostic imaging. Did or didn't I? If I did, but you missed it, okay, well, here it is. Here's the reason why. So we can say, okay, the higher the frequency of our transducer, the shorter the wavelength. Clear? Okay. And what a shorter wavelength will give us? A shorter spatial pulse length. And what would that do? That will give us a lower numerical value of the axial resolution. And what is that lower numerical value of the axial resolution going to do? Is that it will be able to clearly or distinctly display two structures. Although it's okay, there's a shorter distance between them. Now, please keep in mind here, it's okay, for your axial resolution, that distance is going to be when measuring the distance of a structure in front or back. Or more accurately, we can say it's okay, more correctly, or more likely the way that I want to talk about it, shallow and deep. Clear? Okay. So, please, if you haven't got it, once again, if that distance between the two structures is equal or greater than the numerical value of your axial resolution, that would be good. You will have a good axial resolution. Whereas if that distance between the two structures is less than the numerical value, that'll be bad. Did you guys get that? Any questions? Okay, guys. Now, your Excel resolution also goes under 4 other names. OMG. So what have I been telling you guys that, okay, yes, there are going to be things that we come across that will be known than more than, or known by more than one name. And what's going to be your job?
So remember all of them.
To remember all of them. Because, okay, I may ask you a question of Excel resolution, or the way we say Excel resolution from now. Okay? But that can also be referred to as a longitudinal resolution. It may also be referred to as a radial resolution. It may be also referred to as a range resolution. Or, and you can see as, okay, I like the last nor the best. That was right. Okay, because it not only as, okay, gives the name to the resolution, but it also says that, okay, relate that resolution. I mean, it's okay, specifies it's okay what that resolution is about. To be able to just, okay, display structures that lie deeper and deeper to one another. Yeah, okay. No, that's okay. Your book I give you is okay, the formula large. But if you don't want to make large, you can just, okay, switch the letters around as you want. You can make it as, okay, a or whatever. It's up to you. Okay, or you can make it a RALD or whatever. Okay. Or it's okay, your own synonym, whichever, or it's okay, mnemonic or whatever you call it. But these are as okay, the other 4 names that your Excel resolution goes under. Did you guys get that? Any questions? Nobody want to say anything? So the 4 other names of your Excel resolution is longitudinal, range, radial, and depth. Yeah, okay. Now the question just comes as, okay, is your Excel resolution adjustable? No. Because your spatial pulse length is going to be mainly as, okay, determined by the spatial pulse length of your transducer. Okay, and that was going to be fixed. If you look back into just, okay, what we talked about in chapter number 8. Things such as frequency and so on so was determined by as, okay, how your transducer was built, right? especially as okay when we talk pulsed wave transducers, right? Okay, what's going to be the wavelength? The wavelength of your transducer of the cycle of sound wave produced by that transducer was equal to what? Half the
Twice the
thickness,
thickness.
half the thickness of your what? Half the thickness of your
EZT.
PZT. Exactly. Good. Somebody's prepared for Thursday. Okay. Half the thickness of your PCT. Clear? Okay. And then yes, okay, on top of that, yes, okay, the okay. Okay. So yes, okay, if you want to, yes, okay, yes, okay. Have a change of your exit resolution, you need to, yes, okay, use a different transducer. Yeah. Okay. But there is no knob on your system by which you can change your transducer. Sorry, it's exit resolution. Okay, so since there is no knob, no touch function or whatsoever, then it enables you to just okay adjust your spatial pulse length, exit resolution in this case. Yes, okay, that's why it's going to be non-adjustable. Now, dear guys, as far as the typical value is concerned, Hakuna Matata it. Okay, but if we just say it, that's okay, 0.1 millimeter to 1 millimeter. If we say yes, okay, that's the typical value. Now, 0.1 millimeter, what would be our 0.1? What would be another way of saying 0.1? Can anybody express 0.1 in another way?
Is it to the -1 or no?
10 raised to the power
negative.
-1, right? Okay, good. How what would that be then? Now, 0.1 is a decimal form, right? If you express that as a fraction,
1/10 or 1/10.
1/10, exactly. Okay, or 1/10. Okay, so 1/10 of a millimeter. So what did that tell you? That if the distance between, yes, okay, two structures, for instance, yes, okay, was the 10th of a millimeter apart, or more than that, your system will still be able to, yes, okay, distinctly display those two structures on a scan. Okay, as if that was your, okay. Where if it's 1 millimeter, well, okay. And now that's, of course, that's okay, a greater numerical value. So that's okay. In that case, okay, what is it that you will have? You will need at least 1 millimeter distance between the two structures to be accurately displayed. Clear? Okay. So guys, you may get a low number as a numerical value of your exit resolution. But as I said earlier, if the distance between those two structures is lesser than that low numerical value, you will still have a poor exit resolution. If we say, okay, our exit resolution was 1/10 of a millimeter, but if the distance between us, okay, the two structures was 100th of a millimeter, you will still have a poor exit resolution. Did you guys get that? Okay. Now, dear students, please take a breather and okay, try to read on this, and okay, yes, when we come back, yes, okay, we will talk a bit about, yes, okay, what allows transducer to have better exit resolutions than other. Clear? Okay. And so, should we say that I see you guys in 20 minutes? Okay, guys. Okay, guys. Any questions yet? Nope. No questions, no comment?
Not yet.
Not yet? Okay. Good. So what can we say now? Because the question is, what gives us okay, we can say, okay, better exit resolution. Mainly that'll be because, okay, we have a lower numerical value of the exit resolution. So, okay, which is mean it's okay due to a lower spatial pulse length, which we now can say. So we can say it's okay. Better exit resolution is let's say it's okay, a lower numerical value of the exit resolution, which is, we can say it's okay, due to a lower spatial pulse length, which is going to be due to two things. Either or we can say it's okay, lesser number of cycles in pulse. And now what your book says would be it's okay, a higher frequency. But just keep in mind that this higher frequency actually will mean that, okay, as we have a shorter wavelength. which will cause the spatial pulse length to be low. Is that clear? So both of these here will give us a lower spatial pulse length. That was okay as a less number of cycles per less number of cycles per pulse, or a higher frequency, which indirectly that will mean is okay that we have a lower wavelength. Okay, but the reason that they use as okay high frequency here is going to be that, as we said earlier, that high frequency transducers well okay, you have a lower spatial pulse length. That lower spatial pulse length leads to okay a lower numerical value of the exit resolution, which will lead to the exit resolution to be better. Okay. Now, guys, in your book, you may see as okay two things. Well, okay, you see a higher frequency, and as far okay as other factors, that's going to be as okay what they will see as okay less ringing. Clear? Okay. So what do we mean by less ringing? That actually is okay, just going to be as okay accounting for the number of cycles in a pulse. Okay. Now just look at it in this way, guys. Your phone starts to ring. You have a phone and it starts ringing. Ring, that's one ring. Ring, another ring. Ring, another ring. Ring, another ring. Did that make sense? Okay, so the more times you let it ring before you pick up, it's going to is okay, your ringtone is going to complete a greater number of cycles before you pick it up, right? Okay. Now, in some places, it's okay. I don't know. But it's okay, different, it's okay. Places of employment may have okay different ways of okay judging how efficient the staff is. So that's their rule is, well, okay, you should pick up the phone at least. That's okay. It shouldn't ring more than twice before you pick up the phone. They may just pick you up, say, okay, so and so and so, please hold, and then put you on hold. And then you are on hold forever. But at least they pick it up after it's okay, just or no more than 2 rings. That makes sense. Okay, but here it's okay. Ringing is just going to mean it's okay each cycle. Okay. So if you have it's okay less ringing, what that may mean? That you have a lower number of cycles per pulse. Did that make sense? Okay. Now, what was the lowest number of pulses that you can, cycles that you can have in a pulse? What is the lowest number of cycles that you can have in a pulse? What is the lowest number of cycles you can have in a pulse?
Is it 1?
1.
Okay. lowest number of cycles in a pulse. Right here. If it is just one, what is this? You only have one cycle. What would you call the wavelength of that cycle, or the length of that cycle? You have one cycle, and you measure from here to here in terms of distance or length. What would you call that?
Wavelength?
Okay, good. But my question is this a pulse?
No.
No. What is it then?
Cycle?
It's just a cycle. So what did we say a pulse was?
More than one cycle?
It's going to be more than one. So then the lowest number will be at least two cycles. Okay, two cycles will make a pulse. Now, Lily, I know it was not you who said one. So one cycle is a cycle. Two cycles is a pulse. Yeah, okay, then you go 3, then you go 4, then you go 5, then 6, so on, so on, so. Yeah, okay. Well, what's going to happen? Then when you increase the number of cycles per pulse, what's going to happen? Your pulse gets longer and longer and longer and longer. Clear? Okay. Which will mean that if the pulse gets longer and longer and longer and longer, your spatial pulse gets longer and longer and longer and longer, which gives you a greater and greater and greater and greater numerical value of your exit resolution. And the greater the numerical value of your spatial resolutions get, the poorer is it will be. Did that make sense? Okay. Yes, Teresa, you look confused. You sure?
Yeah, I'm processing all of the words.
Okay. Do you want me to reduce the frequency of words?
No, I get it. I'm just like
Okay.
putting everything together.
I can speak slower if you want to.
No, I'm good. Thank you.
No problem. Okay, but please keep in mind here that, okay, yes, in this instance, okay, of course, that's okay when we keep the wavelength, but if we compare, that's okay, a pulse, let's say that's okay. If you compare a pulse with two cycles, each cycle have, okay, the same wavelength, counter to a pulse with let's say it's okay, 4 cycles. Okay, but here's okay, we will have more ringing because, okay, we have a greater number of cycles in the pulse. Okay, that more ringing or mainly is okay cause the spatial pulse length to increase, which will increase the numerical value of the exit resolution. Which then mean that, okay, yes, that we will have to have a greater distance between the two structures for them to be distinctly displayed on an image. Right. But less ringing is going to give us a shorter spatial pulse length. Okay, but the least number of cycles that you can have in a pulse dice is 2. Because for a pulse, or just okay, for something to be called a pulse or a pulse, it has to have at least 2 cycles. Because if you just take 1 cycle, it's just going to be 1 cycle. Did you guys get that?
Yep.
Okay. Any questions?
No,
So the least 2, well, upper is okay. For a pulse, we say it's okay. Some books said 4, some books say it's okay 2 to 6. And as I said, it's okay, some may even go, it's okay 2 to 10. But we made it's okay, just stay with this. Okay, so even if you just had, let's say it's okay, 2 cycles per pulse. Okay, there, okay, yes, the wavelength for each cycle here was the same. Okay, but it's okay. It's okay. This number of pulses is okay. Of course, it's okay. Multiply by the wavelength will give the spatial pulse length. This spatial pulse length, when halved, equals the exit resolution. Which will be having a lower numerical if we had a lower number of pulses. It will have a greater numerical value if we had a greater number of cycles in the pulse. This would have been referred to as more ringing. So by more ringing, we mean as okay, a greater number of cycles in the pulse. Did you guys get that? Whereas, guys, on the other, yes. On the other hand, we say a greater frequency. Okay, but just so that's okay, so you guys can remember that, okay, yes, greater frequency transducers gives better exit resolution. Okay, but it's mainly as okay, just a matter of copy and paste that we say as okay, greater frequency. What does that do? that leads to is okay a lower wavelength. As you also know that okay, as of course this greater frequency here is okay, also is okay leads to lower period. But here it's okay, it's mainly it's okay the wavelength that we will be talking about or reflection. Okay. So if in a transducer you had, let's say it's okay, one cycle, and let's say it's okay, two cycles. Where we for instance, okay, you can say it's okay, can we have a greater wavelength, let's say it's okay, that this distance here was 2 millimeters. But for a pulse, yes, okay, our spatial pulse length, we had been 2 cycles times, yes, okay, the 2 millimeters, which means it had been the spatial pulse length of a total of 4 millimeters. Our exit resolution or had been those 4 millimeters divided by 2. Which would have been 2 millimeters. But in a similar cycle, if we, for instance, okay, say that, okay, as we have a lower wavelength because of a greater frequency, although we still have, yes, okay, only 2 cycles, then that's going to, because that's okay, less ringing still. Okay. But we can say, okay, here, the wavelength is just 1 millimeter. So in this instance, okay, what our spatial pulse number have been is 1 millimeter, which is the wavelength, multiplied by the number of cycles, which was 2. I can do this. 2 cycles, which becomes 2 millimeters. Okay. Now this 2 millimeters, yes, okay, as far as the exit resolutions value becomes is, it's going to be as okay, these 2 millimeters here, of course, it's okay, halved or divided by 2, which gives us okay as an exit resolutions numerical value of 1 millimeter. But where we mainly says okay, due to the high frequency, you have a lower wavelength, the lower wavelength, lower spatial pulse length, lower spatial pulse length, that's okay. Lower numerical value of the exit resolution. Okay. Where we mainly can say is okay, comparing these two here together. This high frequency, we have okay as an A numerical value of 2 millimeters, whereas okay as for the low frequency, high frequency, The low frequency, we have a greater numerical value. Whereas, okay, as for the high frequency, we have a lower numerical value. Which means or mean that in this case, yes, okay, as long as the distance has to be at least 2 millimeters. But these two, yes, okay, structures, which was shallow and deep, to be distinctly displayed. Where here, the distance between these two structures should be, yes, okay, at least 1 millimeter. Or more. As here, it has to be at least 2 millimeters or more. For them to distinctly displayed. So the greater frequency, the lower the wavelength. The lower the wavelength, the lower your spatial pulse length, the lower numerical value of the axial resolution. Which means if we able to, yes, okay, distinctly display, yes, okay, two structures which are at a lesser distance. Here's okay, the minimum distance has to be 1 millimeter. If it was less than 1 millimeter, let's say, okay, the distance here was 0.5 millimeter. Then these two structures here would not have been distinctly displayed. Then it would have to be a poor axial resolution, because the numerical value of your axial resolution was greater than the distance between the two structures. One is shallow, one is deep. There, comparing these two is okay. Where we had a low frequency, that low frequency gave us a great wavelength. Okay, that great wavelength, greater axial spatial resolution, greater spatial resolution, greater numerical value of the axial resolution. Okay, which mean here that, okay, yes, the distance between the two reflector has to be at least 2 millimeters. If it was 2 millimeters and okay, our spatial or axial resolutions, numerical value was 2 millimeters, well, okay, yeah, it would have been good. As long as it was at least 2 millimeters. If it's more than 2 millimeters between the reflector structures here, it's okay, you will still have a good axial resolution. But if it was less, if this distance here is okay, was less than 2 millimeters, let's say 1.5 millimeter, that would mean you're going to call that, okay, as with this space numerical value here, yes, okay, you will have a poor axial resolution. Did that make sense? Or let me play some of you guys in the classroom. Clear? Should we go to a classroom? This is me. I'm the transducer. And okay, yes, I will be producing a pulse. And we can say, okay, and once that's okay, we may have a, oh, let me just do it this way. It's easier to draw it this way. It's me, or it's a transducer, and okay, yes, I will produce a pulse. Well, let's say it's okay, a spatial pulse like this. Now, guys, just keep in mind that what is it that this pulse here will do? It will travel to yes, okay, a certain distance and then reflect back. And what it actually is okay will do when it reflects back. What does a pulse do when it reflects back? A sound wave. It's going to be bringing info from it's okay about the structures that it hit. Clear? Okay. But in this case, yes, okay, this is my spatial pulse line. Now let's just say that okay, yes, this here is okay as the first table at a shallow depth. Let's say this here is another table at a deeper depth. Now let us just say is okay, what a good resolution would have been. Now who wants to sit at the shallow table? Anybody want to volunteer?
Caitlin.
You good? So Teresa is okay, wants to sit on the front table. Okay, good. Anybody who wants to sit behind Teresa?
I'll sit behind Teresa.
You sit behind. Okay, good. That's the spirit. Okay. Now, this was my pulse. We can say it's okay. In this instance, yes, okay. We say it's okay. This will be a pulse with a short spatial pulse length. All that mean that we will have, okay, as a low numerical value of the exit resolution. Which mainly will mean that, okay, yes, this pulse here is okay, travels, dang, 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 dang. Hits Teresa, come back. And what do I get from that? I get this scanning here of and says, okay, this is Teresa. Did you guys get that?
Yep.
Good. What happens next is, okay, yes, this pulse is going to travel out again. Dang, 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 dang. Hit Caitlin and reflect back. And okay, yes, I get that as a reflection of Caitlin that will be produced. Okay, but mainly as okay, we can say as okay, or mainly as we say is that okay, yes, half the size of pulse is okay, spatial and the spatial pulse length. Okay. is, which is the numerical value here, is lesser than the distance between Teresa and Caitlin. That's why it's okay, we see them as two separate reflections on our image. Okay, let's just say that, okay, here is, okay, our spatial pulse then had been 4 meters. As long as the distance between Teresa and Caitlin was 2 meters or more than 2 meters. In that case, okay, we get a good axial resolution. If my pulse was 4 meters long. Did you guys get that?
Yes.
Good. Now, if due to whatever reasons, let's say it's okay that we still have the same pulse. We still produce the same size pulse. Let's say it's okay, 4 meters. I'll call it okay because it's okay. Because it's okay, 2 cycles, and each cycle had a wavelength of 2 meters. But if Teresa, who is still, yes, okay, the one that sits in the front. Either Teresa moved back, or Caitlin moved a little bit closer to her. Okay, now when this big pulse, yes, okay, which was 4 meters, okay, where we mainly say, okay, we still need to have, okay, as a distance of at least 2 meters or more for it to be a good resolution. But what happened here is, okay, well, let's just say it's okay that Teresa moved up, Caitlin moved up, and now yes, okay, the distance between you two girls is only 1 meter. Now when this big pulse here comes, dun, 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 like this, and then reflects back. Well, okay, my dear, what do you get? It's Teresa being smushed up with Caitlin. Now, what that may look like is that, okay, it may look to me like as Caitlin is wearing Teresa's top. Okay, because I can't distinguish between you two. Right? Okay, Caitlin, she got black hair, you got brown hair, that's okay. What appears on, okay, what appears to be Caitlin's head is your hair, or color of hair. Okay, so what is it I get? A mix up between you two, right? I can't distinguish, say, okay, this is Caitlin, this is Teresa. Did that make sense? That was because of that's going to be a poor axial resolution. What caused that? That my numerical value of the axial resolution was lesser, sorry, that greater than the distance between the two reflectors. Did you guys get that? Okay, so that's why we mainly can say, yes, okay. Now, what would I need, yes, okay, to still be able, yes, okay, clearly see the two of you as separate reflectors. I could achieve that mainly as by have a further decrease in my spatial pulse length, which either could be achieved by either as having a lower number of cycles or a lower wavelength, which will lead to a greater frequency. Which means recall that as then my pulse would have been smaller. Let's say it's if it turned out to be as 2 meters, but it is still lesser than, or that it's going to become as a numerical value which is still equal to or lesser than the distance between the two of you, although as you move closer, and I will still have as a good exit resolution. But if the distance between the two of you is less, and I'm a long pulse, I'm going to encroach both of you before reflecting back, and as the system will not be able to as distinguish between the two of you, and it's going to be a mix-up. Is that clear? So yes, a bad exit resolution would be yes, one of those filters where things switch around, right? Okay. Did that make sense? Because which is which and which is which. Any questions? Okay. So a few points that should be noted, guys, is within a resolution, whichever has the lowest numerical value will give us a better resolution. So the lower numerical value, the better the resolution. Right, okay. Especially as when we talk about these three resolutions that I mentioned in the beginning: axial, longitude, lateral, and elevational resolution. For these three resolutions, the lower the numerical value, the better the resolution. The higher the numerical value, the poorer the resolution. Because those numerical values has to be compared to the distance between the structures. Okay, but when we talk axial resolution, longitudinal resolution, radial resolution, range resolution, depth resolution, that distance is going to be as when comparing a structure which is shallow to deep, front to back, or as parallel to the beam's main axis. Those distances. So Teresa, you are sitting in front. Caitlin was behind you. Or when we look at that in a scan, I will, if it was a good resolution, I see you as appearing at a shallow depth, and Caitlin was going to be at a greater depth. Did that make sense? If somebody was sitting behind Caitlin, well, okay, yes, then okay, that he or she would appear at a greater depth because he or she wasn't behind Caitlin. And so, did you guys get that? Okay, so as you go from the top of an image, tick, 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 further and further down, where did it go? Greater and greater depth. Any questions? Now we have a dozen of questions. A dozen, right? Isn't 12 a dozen? Okay, good. Now before we go on to those, is there anybody who has any questions or concern about Excel resolution? Okay. So have I been able to convey the message? Good. Stretch your legs, refill your coffees, and I see you guys, since you guys, well, okay, will be having an ED today. But I see you guys in 10 minutes and we will talk about, we try to just, okay, look at these questions here together. Okay. Have fun today. Okay, guys. Don't go out. It's icy now, okay? So that's at least where it is where I am at. So I don't know about you guys, but it's getting icy. Okay, guys, so let's see if we can get a little more, okay, clear idea about our resolutions. And look at, okay, the questions here. So we take question number 1 and we are talking of, okay, yes, page 147.
149.
Oh, fine, 49. Thank you, dear. At least somebody has a week. Okay. Good. So question number 1. Good. What is the ability to accurately distinguish two structures lying close together called? To distinguish, yes, okay. to distinguish between these two structures here that are aligned close, or you can even say this, that is what you call resolution. Yeah, okay. Now, usually that's okay, guys, when we talk about that's okay. Structures lying close. Yeah, more that's okay, we okay, say type of spatial resolution, which is going to be axial resolution, lateral resolution, or elevation resolution. Now, question number 2. The ability to distinguish two structures lying close together, front to back. Now, lying close together. What we can say is okay. Distinguish between, it's okay, two structures lying close together. But here they go even specific and say it's okay. If that is front to back, or as we said, parallel to the beam's main axis, was what we called axial resolution. But this axial resolution can also be called longitudinal resolution. Could also be called a range resolution. Could also be called a radial resolution or a depth resolution. Did you guys get that?
Yeah.
So all these here were, or we can say, okay, these are the 4 here were just nicknames of our VSOK, otherwise we're just referred to as a axial resolution. Okay, we can say front to back or shallow and deep. And due to this, that's why I mean it's okay. Call it the depth resolution. Question number 3, no axial resolution. Oh, that's okay. Any of these, that's okay. Other names that could also be placed. Okay, is measured using a unit of distance or length, such as millimeter. Okay, so mainly as okay, as I said earlier, when talking about these resolutions, we call them spatial resolutions because, or types of spatial resolutions, because they use or they talk about the resolution or the accuracy of displaying structures lying close together. Okay, by okay, comparing okay, the numerical values of these resolutions here to, which is going to be a distance, to the distance between the structures. Okay. But for axial resolution, that distance was okay when we took the distance of a structure which was in the front to back, or shallow to deep. Did you guys get that?
Yes.
But all these, yes, okay, you will see it as we, yes, okay, go on to the other resolutions. That, okay, as their numerical values are still going to be using a unit of distance. Now again, yes, that distance is still going to be compared to the distance between structures. Okay. But the relationship was how these structures physically are related to one another in placement is going to be different. Okay, guys, question number 4. Now, if there are more cycles in a pulse, the numerical value of the range resolution is going to be greater, less, or same. So one we see here is more cycles in a pulse. What would this more cycle in a pulse mean? That was going to be the same as saying more ringing. Did that make sense? Yeah, okay.
Yeah.
So the phrase more cycles in a pulse can also be replaced by more ringing. But what did we see that as this more cycles per pulse or more ringing here will lead to? They will lead to an increase in the numerical value. So the numerical value would actually increase. How? Roughly, yes, greater number of cycles will lead to greater spatial pulse length in this case. You will call as that you divide a greater number by 2, you still get a greater numerical value. Clear? Okay. Did that make sense? But here, yes, guys, if you look, they use the word range resolution. So again, as I said earlier, it's if you don't know that range resolution is the same as your axial resolution, you may be lost. Did you guys get that?
Yes.
Clear? Okay. So here is due to the increased number of cycles, the numerical value of the range resolution increases. But that greater number of cycles can also be rephrased as more ringing. Question number 5. Any questions, girls, guys? Sorry,
Not yet.
not yet. Okay, good. Question number 5. Now, if a pulsed or if a new pulsed wave or if a new pulse transducer has many more cycles in its pulse, the image accuracy is going to improve, degrade, or remain the same. Now, what they mainly say is, we still have pulse wave transducer. Okay, that is just make you go as anyways, has more cycles. Now, what is that more cycles going to do? That's going to increase the spatial pulse length, right? Did that make sense?
Yeah.
Due to that, that's going to increase the numerical value of your axial resolution. Now, due to an increased numerical value, what's going to happen to the resolution? It degrades. Did you get that? Because all of a sudden, yes, okay, we have a greater pulse. And due to that, yes, okay, Teresa and Caitlin are going to be mixed up. Okay, so that's going to be a degraded resolution. Or because that's okay, less accurate. Okay, if I look at the two of you and I can't clearly see, it's okay, which of you is Teresa, which is Caitlin, then okay, yes, I need to, yes, okay, get my eyes checked. Did that make sense? So greater numerical value, poor resolution, or degraded. And then vice versa. Okay, in this case, it's okay, what causes it to have, okay, it's a greater numerical value, more cycles per pulse. More cycles can also be referred to as more ringing. Did that make sense? Question number, what do we have? Question number 6. And here, mean it's okay, gives us two options. They say it's okay, either high or low. High or low what? Frequency. Transducers generally have the best range resolution. Now, before we go into the frequency factor, just look here again. Range resolution, just another word for axial resolution. What are we looking for here? Best. Clear? Okay. Which requires high frequency transducer. Because this high frequency is okay will lead to lower wavelength, which now is okay lead to is okay lower spatial pulse length, will lead to a lower numerical value of your, in this case is okay, range resolution, but also known as the axial resolution, radial resolution, longitudinal resolution, or depth resolution. Yeah, okay. There's the opposite. A low frequency transducer would actually have led to, yes, okay, the lowest axial resolution or range resolution, or we can say, okay, poor or bad. Why? Low frequency, great wavelength, great spatial pulse length, great spatial pulse length, great numerical value of your range, radial, axial, longitudinal, or depth resolution. And that greater numerical value causes it to be, those resolutions to be poor. Did you guys get that?
Yeah.
Good. Question number 7. Now, which of the following transducer has the poorest axial resolution? So what are we looking for? Yes, okay, poorest axial resolution. Now, just so we know what poorest axial resolution is going to mean, that is going to mean that we have the greatest numerical value of axial resolution. What gives us that great numerical value is greater spatial pulse length, which will mainly mean great number of cycles. and on the other hand, low frequency. So if that's what we are looking at to get the poorest axial resolution, just look at that option. Now, the first thing that we have is frequencies. So we have 1.7 megahertz, 2.6, 1.7, 2.6. So the 2.6s can be crossed out, which means, okay, just leaves us with 1.7 megahertz, right? And then we have to pick the one with the greatest number of cycles, which is, we have 4 cycles and 5 cycles. So the one with 5 cycles. Okay. So a 1.5 or 1.7 megahertz frequency with 5 cycles is going to have a poor axial resolution because of a greater spatial pulse length, which will give us a greater numerical value, which will give us a poor resolution. Did that make sense?
Yes.
Question number 8. Now here we go. Here we talk real stuff. So in soft tissue, yes, okay, 3 cycle, 1 megahertz pulse. Okay, yes. Okay, let's see. Okay. In soft tissue at 3 cycles. So what do we have? 3 cycles per pulse. Okay. And we have a frequency of 1 megahertz. And it is in soft tissues. Yeah, okay. Now has a spatial pulse length equal to 4.5 millimeters. What is the axial resolution? Okay. Now some of you might have to begin with have said, okay, shit, do I need to, yes, okay, calculate the frequency here, the wavelength here, and then multiply that by 3 to get the spatial pulse length? No, not really. They already gave you, yes, okay, your spatial pulse length here. So the only thing that you need to do to get your axial resolution is that those 4.5 millimeters is going to be, yes, okay, divided by 2. So you get a total of 2.25 millimeters. Is that clear? That becomes just, okay, the axial resolutions numerical value for this transducer here. Is that clear, guys?
Yes.
But what would this value here indicate? That as long as the distance between structure to structure here is 2.25 millimeters or greater, we will have a good axial resolution. Whereas if this distance between these two structures here, that's okay, was lesser than 2.5 millimeters, you have had a poor axial resolution. Okay. Because there will be a greater pulse that will come and then reflect back and take these two, which will be appearing as one. because of a distance that was lesser than the half of the spatial pulse length. Yeah. Now option D as in donut would have been the correct answer had they not asked you about the numerical value of your exit resolution, but your wavelength. Yeah. Okay, had the question with all this info here is okay, asked you about the wavelength, then is okay, 1.54 millimeter would have been the right answer. Why? Because 1.54 divided by 1, which is the frequency, that give you the wavelength. Okay. So here is okay, you didn't really, just a matter of okay, yes. Dividing this by 2 to give you this. But this is when we, yes, okay, then compare this number to, yes, okay, to this to determine, okay, yes, did we have a good resolution? Or did we have a poor resolution? If this distance here is equal to the actual resolution numerical or greater, the distance, that would be a good resolution. If this distance between these two structures here was lesser than your numerical value, then it will be a poor resolution. Question number 9. Now, which of the transducers has a best exit resolution? Good or best, whichever. Now, what do we need for a good exit resolution? We need it to have, okay, that's a low numerical value. What is going to give us a low numerical value? It's okay, a low spatial pulse length. What will cause that? Low number of cycles per pulse. And or okay, it's a low wavelength, which was mainly it's okay, the same as saying it's okay, high frequency. So this will mainly is okay, be what we will be looking for. The transducer with a high frequency and a less number of cycles per pulse. So the two high frequencies that we have to start with is 2.6 megahertz. Okay, very main is okay, just can take out the 1.7 megahertz because those were the low frequencies. Okay, whereas in one case, that's okay, we have 3 cycles. And another we have 2 cycles. But what we were looking for was good, so that was going to be less cycles. So this would be the one. 2.6 megahertz and 2 cycles per pulse will give us the best exit resolution as far as these transducers here were concerned. Did you guys get that?
Yeah.
Good. Question number 10. Now, two different transducers create sound pulses. Okay, let's just name them A and B. Okay. Now, one transducer is labeled 5 megahertz. Because we have two frequencies, so it's going to be just okay. 5 megahertz, and the other is 3 megahertz. Okay. Which transducer is more likely to create a more accurate image with respect to the axial resolution? Okay, so they're asking us two things. Which of these two, A or B, have best axial resolution? That's question number 1. Which transducer probably have the lowest or lower numerical value of the axial resolution? Now, guys, as far as we know, for SOK, best axial resolution, high frequency. Right? Okay. And now, why and how? Well, okay, high frequency. Sorry. Low wavelength. Low wavelength lead to a low spatial pulse length, and which means, okay, we'll answer our next question, which will be low numerical value of axial resolution. Did you guys get that?
Yeah.
Any questions so far?
No?
Good. Good. Question 11. Now, two different transducers create pulses. Both transducers create. Okay, so we have again, yes, okay, we can say it's okay, A versus B. So they both have frequencies of 4 megahertz. So the frequencies are the same. One transducer creates a pulse compromise of 6 cycles. And the other 3 cycles. Okay, which transducer is more likely going to create the more accurate image with respect to axial resolution? And which transducer has the lower numerical value? Now, guys, now the frequencies are the same, but what we have here is more cycles, so this will be more ringing, that's what you want to call it. Whereas this one here is going to be less ringing. Is that clear? Now, since the frequencies are the same, that's okay. So the wavelength is also going to be the same. So with that said, this transducer here will have, okay, as the lowest numerical value of axial resolution. And due to that, will also be the one that will produce a better axial resolution. Contrast to this one here, will have a greater numerical value of the axial resolution, and due to that, be a poor axial resolution. Did you guys get that?
Yes.
Now question number 12. Now two transducers create pulses. One transducer layer with 5 megahertz and the other is 3 megahertz. So you say A and B. 5 megahertz and 3 megahertz. Although it says that this fellow here has a better axial resolution. Because says, okay, this one here will be as okay, a poor axial resolution. And the question is, why? Now what we can say from yes, okay, the high frequency is it will have a lower wavelength or a shorter wavelength. Whereas, okay, as this lower frequency here will have a greater wavelength. Yeah, okay. But the only reason that can explain why it's okay, this dude here still has the better axial resolution is because of the lowest or least ringing. That this pulse here actually is okay, might be as okay of a lesser number of cycles. Whereas this pulse here, although it's just okay at higher frequency, which gives it a lower wavelength, and okay as a greater number of cycles, which gives it okay as a greater spatial pulse time, which gives a greater numerical value, which gives a more axial resolution. That makes sense. Well, that's okay, as you guys may know. Your tests are not open-end questions. Okay, dear students. Unfortunately, I have to let you guys go earlier than otherwise reasonable. But it's not a go out day. So stretch your legs, get your green book, sit by the fireplace, enjoy a cup of coffee and your book. And hopefully tomorrow is okay. I would expect you guys to be bubbling with questions. Yep. Okay. Any last words about Excel resolution? Good. So bottom line is good Excel resolution, no problems. Poor Excel resolution will lead to problem which we will call artifact. So the outcome of a poor resolution will be an artifact. The artifact that we got earlier was that, okay, yes, I'm mixing between Caitlin and Teresa. Okay, so one of the reasons for your artifacts is poor resolutions. Not just Excel, but even yes, okay, the other resolutions. Have fun. Enjoy the evening or whatever is left of the day. And I will see you guys tomorrow. Okay.
See you tomorrow.
Okay. God bless.
Thank you.
Bye-bye.